Okay, so we have, this is the first pedestrian or student seminar of the year. This year is the time of Roger. He's going to talk about collider physics, color physics and hadron collider. And we hope that everybody's going to understand. Any question, please ask him. He's going to try to be most academic as possible.
Yeah.
Okay. So, welcome. Thank you.
Stop me every time that you want. So I'm going to talk, as Roberto just said, about color physics and hadron colliders. So the outline of the talk will be, I'm going to give a brief motivation, where did the color physics started, where you can find it. Maybe all of you know it, maybe you have to, just to remind a little bit. Then how did you include the color in the standard model, and particularly I am going to talk about the quantum chromodynamics with the perturbative calculation and the non-perturbative one. And at the end, I am going to give QCD phenomenology. One of the most clear examples, it will be the Higgs discovery. And I'm going to show you how it was, since the QCD point of view, it was discovered. And then I'm going to give some brief conclusions. So the question is, why do we need to study the color physics or quantum chromodynamics? This is simple. The new physics is going to be studied, which is now studied in Hadron Colliders. They are, QCD is one of the main, or this is the most important processes are given by QCD process, initiated and in the final state and in the initial state. So you have to understand all the properties in order to give some predictions. So QCD dominates all the production mechanism, because whenever you start, for instance, in the LHC or the tevatron, they started with protons or antiprotons, as in tevatron, and the protons are made of something small. These particles are going, as you might know, are the quarks and gluons. But also QCD is the main background. So then whenever you start with the initial state, it will be a proton. The proton is made of something else. This something else is going to be quarks and gluons. So then you have to extract one of these partons, and then you have to make them interact, and these processes are not, it has to be understood within the quantum chromodynamic framework. So, but how we started? Well, at the beginning you have known that in nuclear physics, for instance, you have the decuplet and the octet. The octet and the decuplet are made of single blocks, which are now known by the quarks. And this was proposed in 1964 by these two gentlemen. And so you see that these partons are made of U, D, S. Also, you now know that we have the charm, strange, the top, etc. And we know that this decuplet, for instance, if you look closely, these are bounded states. We know that with this tree, for instance, this tree U, you find the delta plus plus, or also with these three different quarks, you find the omega minus, for instance, which is completely different, you see? There's something more important. So you have the y-axis, the I3, the isospin, and then here is the charge. If you look in this direction, you have the charge of the particles. And this is also known because of if you start with the SU3 building blocks and you start to build the wave functions. So all the wave functions that you have you can write down, they are called basically two different type of groups. If you find a bound state made of 3 quarks, they are called baryons. And if you find a bound state made of 2 quarks, they are called mesons. And all of these subatomic particle, let's say the fundamental particle, you know that is the up, the down, the strain, the charm, and bottom, and the top. And all this you cannot see here, but this has to be written omega minus, and here is the jet psi, and the epsilon. And all of them have been proposed and discovered. So then this is one of the key points. So the question now is, well, if everything is okay, why do we need color? The problem is that if you look, well, here is what you can find on the PDG. You have the U, the electric charge, the mass approximately. In MEVs, this is really small in comparison with the C or the Z or the W mass. And then, but what is the problem? Well, so we have a problem here because you know that the delta plus plus is made of U quarks, all of them with the spin 1/2. If you add all of them, you have 3/2. Well, it doesn't matter. But the thing is that if we return back a little bit and you can find the charge, sorry for it. If you add, we are looking at the omega minus. If you add the three S quarks, the electric charge will be minus. So it's okay. We found it in the 64, but the wave function is completely symmetric. And so we know that it's a fermion, so there has to be an antisymmetric something. And so it's forbidden by the Pauli principle, but you find it in nature. So something is wrong in the theory. So what's the solution that they propose? So then you have another color. You have another quantum number. So just add antisymmetric Levi-Civita tensor, and then now the complete wave function is completely antisymmetric. And so it's well understood because of the Pauli principle, and because all of these are fermions, right? So now everything's said, but I am going to talk about a Hadron collider. What is a Hadron? If you go to the PDG, the Hadron, and also in Wikipedia, they were going to tell you that it's a particle made of quarks in a bounded state, but they are bound by the strong interaction, by the color. And they are divided into groups, baryons and mesons. Baryons, for instance, protons. So we are going to collide protons, we are going to collide baryons. And we are going to produce, for instance, mesons like pions and kaons. The detectors are going to measure the energy momentum of these particles. Of course, the detector will not going to tell you this is a kaon, this is a pion. They will going to tell you what is the energy and the form momentum, let's say. If you square it, then if you find the mass of these particles will be exactly this, then you have a link between the particle and the identification. Not always you have this, but in many cases you have the detectors are like built in the way that they stop some kind of particular particles, like pions, kaons, or whatever. So naively, I put here naively because if you go, I have already said that the protons are made of 3 quarks, and for instance baryons are made of 3 different bound states made of 3 quarks, and mesons like 2 quarks. But in reality, that's not true, because you know that we are going to talk about a quantum physics. So in quantum physics, we are not determining precisely if we have 2 quarks or 3 quarks. We have all of the possibilities. And this is what we find in the distribution functions. This Parton distribution function will tell you that when you are in, this is the energy scale, so it varies this x times the Parton distribution function anyway. So you see that you have the probability to find all of the quarks. Of course, if you add all of them, if you integrate the probability distribution, they were going to tell you 2. If you integrate, for instance, all the distribution of U, and it will be 2. All the distribution of D, it will be 1. And then all of the others are 0. This is something, this is a sum rule, and that's why you have the valence quark will be the U and D, as like in solid state physics, you have the valence quark and the C quark. So then all of these other ones, D, U, S, C, and the gluon are going to be like the C in the proton. The problem is that every time that you go higher in energy, then you are going to reach levels in which the gluons are going to be more dominant. So in the LHC, the energies of the LHC, that's why we call it like the LHC is a gluon machine, because when you try to collide with a very huge energy, then the limits in which you are talking about each where the gluon is very high. So it's like if you take a picture of it, you're going to see a lot of gluons. And then they're going to start to if you let them evolve, they are going to be condensating in all the particles, and then you're going to arrive in a region in which the dominant one will be the U or the D. And so then we call it Parton's distributions, and we say now, every time that I say I'm going to talk about the LHC, they are going to be not only quarks, but also gluons. So we are made of quarks and gluons. And so the valence quark would be the 2u and 1d would give you 2/3 minus 1/3 will be the charge plus 1. So, how do we put all this information in the standard model? So you might know that the standard model has four pieces. This is the gauge piece, which is going to be like the SU3 times the SU2 plus the U1. Here is where the symmetry is not broken, of course. Then we have the Dirac, which is only the term, but also in the covariant derivative you have hidden also the interactions. And you have the leptons and quarks, singlets and doublets and triplets, whatever. And then here you have the Yukawa ones, and here is the Higgs potential. I'm not going to talk about all of this, but only the pieces where I am interested in, which is going to be the quantum chromodynamics. Anyways, one thing that you might notice, and one of the things that in the Lagrangian is very interesting, is that all the signs here are positive except this one. As you might know in the supersymmetric theories, this is going to be positive, but when you go to do the renormalization group equation, these parameters are going to turn to be negative, and then explain dynamically here the symmetry breaking. Here not. Here in the standard model it was put it by hand, the negative sign, and everything's work together, and it works okay. I'm not going to talk about this thing, but anyway, there is some issues in the standard model which are going to ask to other collaborators, and then you will see that there are some topics that are now under studies because they are not the full, completely understood some of the areas in physics. Anyway. So the matter field, you know that you have the doublets, you have the singlets, doublets, and in the color space, these sometimes I have singlets in the color space, they have triplets in the color space, and singlets in the color space. And if you ask, you also can do some very nice calculation if you put the Y1, Y2, Y3, Y4, Y5 for the SU, for the U1, and then you ask for a gauge invariance and anomaly cancellation, you finish with the usual quantum number of U1. Of course, you have a normalization. You can give a 1/2 normalization for the algebra of whatever. But anyways, if you take out this normalization, then the parameters are fixed. And the strong interaction is going to be by quarks. Here you have, for instance, what we say that the quarks and the gluons are the strongly interacting ones, and then you have mediated by the other gauge bosons, and then you find the leptons. And then, but in between them, the quarks and the leptons, they don't mix. You have to pass through the gauge boson, and then if you want to see something interesting with the leptons, you have to always pass through these gauge particles interactions. So what is the QCD? QCD is very simple. QCD, the idea is very simple. So the fundamental principle in the old standard model is the gauge invariance. So it's exactly the same, but now in QCD, the local rotation is going to be the local rotation on the SU3. So meaning that if you have 3 different colors, then you just only make a rotation, and at the end you finish with this. But the property is that the Lagrangian is still gauge invariance. It's still invariant under this transformation in the color space. So quarks are fields of the spin 1/2, and they are arranged as the color triplets or singlets. And due to the unbroken symmetry of SU3, then you have 8 massless bosonic particles, which are now we know that they are the gluons, and they interact between quarks and themselves. The non-abelian structure is like this. It's like in the SU2, just like this matrix is 3 times 3, and you have also the FABC antisymmetric tensor. Anyway, you have the number of colors at 3, and CF and TF is 1/2. This is the normalization, and this is n squared over 20.
What is CF?
CF is CF is one of the when you do a computation in QCD, always have the number of colors. For instance, this is going to be exactly the number of colors. and this is the number of colors squared minus 1 over 2, over 2. And then this is the normalization, which is, it has to, well, here in this relationship, TF is here, but it has been chosen to be 1/2. So you don't need to put here a TF for the delta. Anyway, so the physics of the strong interaction, for the LHC, can be described by the QCD Lagrangian. This is the Lagrangian that we are interested in. So you have here the propagation for a massive particle, which is going to be a line, you know. So this is the F mu nu, so the propagation of the vector field. And then here you have the interaction, the vector and the fermion. Here you have the 3-point interaction between the 3 fields, and here you have the 4-point interaction. This is something which you don't have in QED, for instance. And this is without fixing the gauge. So everything that you have to understand here is that when you start with QCD, then you only need these rules. The problem is that in order to have these terms in the quantum field theory, you have to do an expansion over something in order to have this propagation. So remember that when you study the Peskin or whatever book of quantum field theory, you say, okay, I'm going to, in my mind, to say I'm going to start with one particle in this point, and it's going to propagate, and I'm going to annihilate this one on the other part. And then this sandwich or whatever bracket you made up, then you have the evolution operator. The evolution operator here will be the exponential of minus I over h bar, like the Hamiltonian, like classical mechanics. The problem is that in electroweak theories, so the coupling is the parameter where you start. The assumption of this parameter is going to be small, and then this parameter allows you to write all these Feynman rules. In QCD, the problem is that the running of the coupling is not that simple. So the coupling, there are some regions in which you can believe that this is going to be true, but in other regions are not true. So what am I saying? So the problem is, can we use QCD in all the energy in the whole energy range? The answer is no. So we have, from one side, you have the confinement. The particles I was telling you is that they are condensate, they are bound states, and in this bound state, the particle feels really the coupling is really high. The strong coupling is very high. But in the other side, when you imagine that you collide two protons at 14 TeV, like in the LHC, in 1 second, millisecond, or nanosecond, whatever. So just in that time, the particle will be like free particles. So in this time, you say, okay, in this moment, my perturbative series is okay. But when I am going to detect the particle is going to travel sometime, and then they're going I am not going to detect free particles. I'm going to detect condensate particles. So this transition between one side in another is what we call the asymptotic freedom and the confinement regime. Both of them have to be perfectly in agreement. So, and we now believe that this is something which has been proven. Some of the things that I'm going to show you have been proven experimentally, because theoretically they are not proved yet. But experimentally we show, for instance, the factorization that I'm going to show in a moment, that it's true. And anyway, you have to, I just only want to say that any theory that you want to test, you say the calculation, and then at the end you go to the experiment, and the experiment will tell you it's okay or not. If not, okay, next. So this is one of the checks of QCD. So here are the evolution of the strong coupling constant. It's not 10 to the 16, so we do not know about Guts theories anyways, but you can see that in some regime alpha strong goes very high, close to 1. It's not like in QED, but then in another regime they're going very small. So this is the confinement, and the other one is the asymptotic freedom, where the coupling is very small. Then you can use perturbative QCD, but if you want to do some prediction of the LHC, you have to run this coupling and all the parameters into a regime where the perturbative is is not well understood. But anyways, everything is, let's say that, under control. So what is the idea that you should keep in mind? So a strongly interacting theory, like in the confinement regime, could become a weakly interacting when you go into higher energies or very small distances. When I want to say small distances is that, well, if you have a microscope and if you want to look at this, then you go really very small distances. You look into very deeply inside the proton, deeply inside one of these condensate states. And so then, this is an enough proof of the perturbation of the theory, and particularly the Parton model. The Parton model will be the complete QCD theory. And the answer, of course, is no, because, as I already mentioned, asymptotic freedom only allows us to compute interactions at short distances with very high energies, and the detectors are located very far from the interaction point, so they have to travel. And moreover, experiments have not detect a quark. They will detect condensate states, or in the let's say that in the better case would be like electrons or photons, and these are well understood. But if you want to analyze hadronic physics, which are going to be mainly in the core of the detector, you have to go into these problems. So that's what they build the LHC. No? If you go to the Wikipedia, then you find the LHC. Everything is very nice. You will see also, this is the most famous plot. You have the LHC, the control room. If you haven't been there, it would be very nice to look at. This is the Atlas, this is CMS, this is LHCb, this is IBIS. No, this is IBIS, and I think that this is LHC. Anyway, this is the complete LHC. So now the problem is that you have in your mind the ideas, but what is the problem? You have always problems anyway. If not, you will not be here. Anyway, in order to establish a connection between the theory and the experiment, you need two ingredients. You have to control infrared divergences in a calculation, hard calculation, and the factorization theorem has to be held in all the process. So the problem is that there are quantities which are independent of the physics at very large distances, and then in this regime you can compute perturbatively the cross section. And the other problem is that when you want to say, okay, I am going to make a prediction, then the factorization that I'm going to use in order to hold all together has to be true. And we do not know. We use it, and at the end, it turns out that it holds. But theoretically, if you want, there are some proof in some particular processes like E plus and minus collision and semi-inclusive deep inelastic scattering, where the factorization it has been proven. But not in all the processes. For instance, for the LHC, it's not proven, but it's used. And when you make a prediction, then it turns out that even with the very small experimental errors, it holds. It still is true what they are measuring is okay. So then the thing is that if you want to have an understanding of this factorization, you have to put into the code, into the calculation, some of the distributions that has to be taken from global fits. You have to run codes, and then you have to compare your prediction and with the theory by let's say by adjusting some parameters of this part of this distribution. You start by saying that, okay, I'm going to say my distribution would be like 0. They have to go to 0 when a value goes to infinity and the other goes to 0. Like a normal, let's say, condition for the best space, no? Have to be finite. Cannot be infinite. And so then but there's a lot of possibilities to do this, to have these conditions. So that's why you have this
But the problem, not the problem, but they say that the agreement that they use is that this has to be universal. And the idea of universality is like, if I go into one of these distributions, the definition is that what is the probability of finding a U quark into the proton? And it doesn't matter if the proton goes from semi-inclusive deep inelastic scattering, if it goes from a hadron-hadron collision, or if it's produced by some other process. The idea of universality is that it doesn't matter the process, the probability to find into a proton, one of these quarks is fixed. When I say, let's say for a q squared equal to blah, or a fractional momentum equal to blah, if I fix everything, the probability is going to be the same. It doesn't matter what was the process that I started with. So what is the problem of QCD? QCD cannot be solved exactly, so then that's why we used perturbation theory. The coupling constant is large, so at the LHC energy, so then we need higher orders in order to increase the accuracy of the theoretical calculation. And there are other problems, like in the Monte Carlo simulation and in all of these analysis made by the theoretical groups, which are really needed for the LHC. If the LHC do not have this calculation, they do not say anything about physics. So here is the advice. Go on your risk. So I'm going to talk a little bit, I'm going to sketch some of the things that you have to know a little bit about how to compute, how to go into perturbative QCD, and then how to deal with the non-perturbative, and then how we mix all together. It's going to be very simple, and if you know already, I apologize. If you want more information, we can discuss later. It's not a problem. So the first thing that you have to know is that in perturbative QCD, we are going to use dimensional regularization. As maybe you already know from your lectures in quantum field theory, you work in a Minkowski space, 4-dimensional space, and then here the problem is that every time that you have 4-dimensional, you have infinites appear everywhere in the calculation. So what we do is that we do not fix the dimension, but we say it's going to be a d-dimension. We say, okay, if you have an integral, you all have integrals everywhere, then you say, okay, this integral is not going to be in 4 dimensions, it's going to be in d dimension. And when you do the calculation by hand, they are going to appear poles. We know that d is equal to 4. But when you have 1 over d minus 4, if d is equal to 4, this is going to explode. So then, okay, I have to deal with this. And before put d equal to 4, let's see if we can take it out from some other contribution, or if I'm going to hide into something else. But that's the main idea. We work into a framework in d dimension, and before set d equal to 4, then we take it out. And then our job is to extract the finite parts in all order. Leading order, next to leading order, next to leading order, next to, etc. But what is this n leading order? So, phenomenologically, as I said, you have the cross-section. The cross-section you can compute, there's no problem. And then the cross-section, it would be proportional to alpha strong. And remember, alpha strong could be very high or could be very small, depending on the regime, depending on the running of the coupling. So the thing is that when you sum, this is a number which you can find on the PDG. It's a fixed number, it's not infinite. The experiments give you the number, they don't give you anything more than that. The problem is that if this alpha s is very high, could be that this piece is not relevant. And for the Higgs, that was the case. If you go for the calculation of the production of the Higgs, then you will see that the leading order have a contribution from the next to leading piece, which it will be this one, which was this twices. So you cannot neglect, because this coupling is not small in all the regime. And moreover, in the LHC, this is high. And so then I am going to show you how to compute the ideas, just the ideas of how to implement a QCD calculation. Let me just say that, for instance, this is the main process for the production of the Higgs at the LHC. I have said several times that gluons are that the LHC is a gluon machine. Then you have to pass through, remember, in order to have, this is the Yukawa, right? So then you have the glue coupled to this straight line, the fermion line, and then you close it with the Higgs. I'm going to put a cross in order to not write the triangle. This is for the gluon-gluon Higgs process. So this is for at the amplitude level. When we say that this is a leading order piece, this is just only this one. There are two things that you have to notice. The first of all, this is proportional to G strong, and then the phase space. We have a processes which started with two particles, and it ends with one. The other part, I call it next to leading order, because remember this is the amplitude level. Then I have to square it. I have to square it. When I do this is the real correction. The problem here is that you have two particles in the initial states, and they have two particles in the final state. So in the phase space is 2 to 2. It's different topology. And you have the virtual correction. The virtual correction, it's two particles in the initial state and one in the final state. When I let's say, if I square, you might think, okay, but this is a different process like this one, because I'm not producing a Higgs plus something else. I am producing only a Higgs. I am saying glue to Higgs. But here the thing is that these contributions, the problem that you have here is that detectors have not infinite resolution. So there is a piece from this Feynman diagram in which if the detectors see all these like one particle, you cannot disentangle it. Then you have to add all together. Here there are going to be some divergences, and here there are going to be another divergences. And then when you add these two, they cancel one to one. So if you go to next, and this is the real correction, virtual correction. If you go to the next to leading order, then you have the double real correction to the virtual real correction and the virtual correction. So then you have here the phase space is different. This is 2 to 3, this is 2 to 2, and this is 2 to 1. So if you want to say, okay, everything is fine, I am going to compute the Higgs production started by the gluon-gluon channel, because you can also have the glue quark or QQ bar, because remember that a proton have also quarks and gluons. Then you can also the combination of quark and gluon and QQ bar, quark anti-quark. So if you want to give the total cross section, then the cross section will be the sum of the leading order piece plus the next to leading order piece and the next to leading order piece, so on and so forth. Where the next to leading order piece will be the integral over the virtual correction plus the integral over the real correction. Let me tell you something. Here you have an extra momentum, and the extra momentum is going to be represented integrating the extra particle. And at the end, if I take out this extra particle, it will be, I will have a contribution to this 2 to 1. Here the problem is that you have a momentum that it runs into this loop. And the problem is that this momentum could go from 0 to infinity. So when I say, okay, here you have an integral here I have also another integral, but the integral that I'm going to implement here is different from this one. This is going to, from one of the loops, one of the loop momentum is going to run here, and this is not the same thing. So that's why you have here, for instance, this omega goes from all the other final state particles. Here, you integrate over the final state particles, and here you have an extra radiation, an extra particle in the final state. And the next to the another will be the double virtual correction. It will be two loops running, two momentums running into the loops. And then here you have one real and two reals contributions. And at the end, you put here, and then it will be as simple as this. It's not like this. But divergences appears everywhere. So then, when you add this part, this piece, plus this piece, the divergences cancels. So you keep it like, you keep it with D or epsilon poles, or because in the literature you will see that the D is equal to 4 minus 2 epsilon. It's another parameters anyway. If you keep it like D minus 4, then you take it out. This parameter will cancel the contributions coming from this one plus coming from the other one. So, is this cancellation just luck? The answer is no. All the singularities in a mass, this is known by the KLM theorem, all the singularities that you find in a massless theory, like UCT, cancel when all degenerate states are added. The degeneracy could be in the initial and in the final state. You have to add all of them. And the thing is that experimentally, a parton with large transfer momentum, meaning a jet, cannot be distinguished between a parton plus a gluon with a small momentum. If the momentum of the gluon is very small, then it could be confused with into the jet cone, because they have a recognition of the cone algorithm. And the other possibility is that if you produce two particles in the final state, and you set the size of the cone like this big, for instance, if the two particles goes inside collinear, they will be like a jet. It will be exactly the same. So that's why you have to take into account the two configurations. If you have two particles going collinear and two particles, but one of them is soft. And these three people have already proven this sentence. So in the basically this is the perturbative case. The non-perturbative case is like this. So then you have some partons coming into this blob, and after hard scale factorization, you cut this integral. You cut this process. So then this is going to be, this part is proportional to this parton distribution function, like I said, and this instruction function that are proportional to the energy momentum that has been transferred. The thing here is that when you imagine that you have a proton, you know that the proton has 7 TeV energy, for example. But when you take one of the partons, you will not take 7 TeV. You take a proportion of this 7 TeV. This is the fractional momentum that you take. And so then these parton distributions are proportional to this fractional momentum, and we have this factorization scale, which gives you the validity of the theory. At the end, you can vary the factorization scale and also the renormalization scale, and at the end of the calculation, these two parameters should not have any influence on the final result, because they have no physical meanings, just theoretical. This is not the unique way to separate long and short distance. They have so many groups trying to take or to extract these functions. But anyways, you have the parton distribution function, which are for long distances, and they are going to be matched with the structure function, which has to be computed in perturbative QCD. So let me just say, so then the factorization determines the limits of the validity of this breaking of the factorization. This is some other things. So when you have some singularities, some of the singularities are going to say, okay, these are going to be hidden or eaten by these distribution functions. And the parton densities, as I said long ago, the probability to find a particle with a certain amount of fractional momentum at some transfer energy Q squared. The definition is something like this in the NS-bar scheme. And the most important thing is that this parton distribution cannot be obtained from first principles. There is no way to say, okay, because I am trying to say something in the regime where the perturbative QCD is not valid, is very at long distances. At that regime, the QCD they cannot be. We have some doubts of the validity. Let's say we know that they are true because of the prediction that we have on the NFC, but theoretically they have not been proven yet. So QCD phenomenology. How we do phenomenology? The question is everything said? We now know how we start. We start with two partons, with two particles, two hadrons, and then at the end we are going to detect hadrons or other particles. And if we know everything, we'll be like very happy, but the problem is not, because experimentally we all do integrals in the 4 pi solid angle, and the experiment they do not have this facility. You have a pipe going into one direction, you have to take it out. From the integral, you cannot count on this side of the detector. The resolution is not finite. They have a cone reconstruction. They have some, not all of the parts. You can't have a bunch of particles crossing into one thing. It's not that simple. The simulation of the detector are not perfect. They have some efficiencies because you have to take everything into account. And they have also different thresholds. They cut some of the data sets. So then all the integrals that you find in the books, the numbers, pi or whatever, they are not, they cannot take in. You can, let's say that if you have a perfect detector, then you can use all the formulas, and then you find out the cross-section. But here, the experiment, they are not going to give you the cross-section. They are going to give you the distribution, because they apply some cuts, and they count the number of events, and they just only make a histogram. That's all that they do. And then when they implement the cuts, and when they pass all these the cuts from the data points, the data sets, then they find the distribution, and then compare the theory. If the theory is correct, they should have, or you should count under certain amount of data points. If they do not, then something is wrong, or something on your theory is missing. So what we do is that simulation in order to recreate the condition at the LHC, and these simulations are performed by using the Monte Carlo method. So the example that I'm going to sketch is the production of the LHC. So the Higgs has been discovered with the combination of the theoretical prediction and the experimental data set. So you have a very precise measurement, but you also need very precise theoretical prediction. And so in 2012, they achieved the 5 sigma statistical significance, which was needed for claim discovery. But how was the path to discover the Higgs? Why it was so complicated? First of all, you do not measure the Higgs, right? You measure the products of their decays. So one has to be able to separate all the contribution from the Higgs, from all the channels, and then in order to do that, you have to have the Monte Carlo simulation from all the channels at the same level of accuracy. So what are the decay modes of the Higgs? Maybe you all know. You have dB bar, WW, ZZ, blue, blah, blah, gamma, gamma, etc. Tevatron, they have very good detectors for leptons. So then, when the W decays into a lepton and a neutrino, this is going to simple for them to look at. And if the Higgs goes in the pair of Z, they're going to the golden modes. We're going to, after the Z decays into 2 leptons. So the golden modes was discarded in this channel because it was not discarded, but they do not look at the resonance there. So then that's why, if you compare this is the theoretical prediction, right? Everything here is theoretical. what I want to say is if the Higgs had a mass of 200 GeV, then you expect that everything goes into a pair of neutrinos plus missing energy, or a 4 leptons. If you do not find this, that means that this 200 is ruled out. So then you have to go into the whole regime to scan over all this regime in order to say, okay, this is the Higgs. So that you can imagine, you can say, okay, the basic one would be this, right? Because everything goes into pair of W's. Everything has to, it would be like an excess, a huge excess of a pair of W. And if I have a detector that detects leptons, they will be simple. If the Higgs have a mass of 160, which was not. The other side was if the Higgs mass was very small. If the Higgs mass is very small, then everything goes into a pair of BP bars, into a pair of Bs. What is the thing of the Bs? The Bs in the detector, you look, and it's very simple. Then you produce one B, and then it travels, and then you can look at the distance that it travels. They have a lifetime. So if you look at the lifetime, and you measure the lifetime, you can say this was a B. And so then there was not another way. So it was simple in this sense, very low energies, and you have to look at the tracks into the detector. You do not look, you look that, and you count the number of events that you look at, and if you don't, what happened is that they didn't find any significance at that level. The problem is that the Higgs was here. That was the problem. The problem is that there was a mixing between the pair of W, the pair of B, the gluon, the Z, and then you go deep inside, you find this pair of gamma. This pair of gammas was the most significant channel for the Higgs. So why? Why? Because the background that you have here is very high. This is also huge, and the photon, you will see a pair of photons very simply. So then what you have to do is like cut all, you have your data points, whatever data point you have, then you cut everything, and then you look at 2 photons. And if you reconstruct the 2 photons and you find at the mass of the Higgs, you count the number of masses of the Higgs that you ended up. And then you have a distribution. But what you really need to do is to separate from one run all of the channels, because in one run you will have 1,000 and 1,000,000 of events. So you have to really, because everything is going to occur, all of the channels are possible. But the more probable one will be the pair of W, then the pair of B, but the background is huge. Then you say, okay, the significance will be smaller. So then I have to go down, 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 down. And this channel is, if you see the original papers from the discovery of the CMS and Atlas, which I'm going to present in a moment, it's not now anyway. The channel that they show is the pair of gammas, because the bump that you will see is only achieved on that channel. On the other ones, no. How we translate the theory and experimental together? Then we have this let's say, idea. You have the incoming particles are protons or hadrons, whatever. Here at the LHC, they are protons. Then one of the partons, which are inside this blob, goes into the hard process. This process I can compute in the perturbative case, which is this one. I can compute this, and this is called the parton level, the partonic level. At the moment that I took one of the partons from this blob and one of the other particles from the other blob, and then I add them together and I say, okay, I'm going to forget everything else, and I can say, okay, this part is going to be used in perturbative QCD. The other parts are the non-perturbative parts, which are the parton distribution function and the fragmentation function. Without the convolution, you have to make a convolution of these 4 pieces in the most general case. And so then you have to add all together, and then you compare. These are the distribution that experimentally you will see in a plot. These are the plots on the experimental side. These are the theoretical side. So then you match them together. And if you say this plot divided times this plot, it will be equal to 1. Has to be equal to 1. in between the error bars. That's the thing that you have to keep in mind. So the integrals are not as simple as this, but anyway, this is the idea what you have to keep in mind when you want to do automatic QCD or QCD computation. These are the plots that I was mentioning. Here are you see that the bump that they look at is in the Higgs to gamma gamma channel. And then here also, here we'll see mass of the gamma gamma. Also the plots or the figures that they show taken directly from the, let's say that from the detector, you will see 2 gammas, because that was the the cleanest channel. And the significance of this, you will see that here, if you say the plus, how do you, let's say, understand this plot? This is very simple. Then you have the data points. After making all the cuts, you have the cuts in the PT distribution, in the rapidity distribution. You add the PDF uncertainties. You vary all the parameters, and then you blah blah. And then at the end you have these points. This is a distribution, right? This is a distribution. And then you go to the theory side. You have 2 options. Or the Higgs exists, or the Higgs doesn't exist. If the Higgs doesn't exist, then the plot, the line will be not showing anything. Do you do the Monte Carlo with the Higgs? You do the Monte Carlo without the Higgs, meaning the background. And then when you add the Monte Carlo with the Higgs, then it says, okay, it will be exactly the same, but at this resonance you will see a bump, which is exactly the same here. You will see the background will be without the Higgs. The background is everything without the Higgs. What I wanted to prove is that there is the Higgs. Well, I know the experimentalists and the theorists, but I didn't do the calculus. Anyways, if you want to do the signal plus the background, meaning without the Higgs plus the Higgs, then you will have to recover this bump. And that's what they did. And that's what they found. After discriminate all the other channels, after looking at all the channels, they do exactly the same, but the bump was only shown in this channel. So are we done? The answer is no. This is another plot. The complete understanding of everything has to be done in all senses. The thing is that when CMS showed the discovery of the Higgs, they had this plot, also from the distribution of the gamma gamma. This has to gamma gamma. It was just an overlap. And you can see that here are the data points, and here are the theoretical predictions. The problem is that they do not fit. They do not match, let's say. It was not a problem at that time. Now there is not a problem, of course. At that time, it was not a problem. The thing is that it was explained that the significance that they achieved was phi sigma. So then there was not another problem. Everything was so under control that this was, let's say, that was not too relevant, let's say. But then they come another group. This was next to linear order calculation. If you go to next to linear order, that means that you add the 3 pieces that I show you on the bottom line of this at the amplitude level diagrams. Then they figure out that they match. And this kind of behavior was shown also at the Tevatron experiment. They have some regimes in which QCD was not accurate enough in order to touch the data points. But now we understand that if you want to say, okay, here could be new physics, it could be. But in order to say that, you have to add as much as you can all the QCD contribution, because they could be very, very large. And not only for the LHC at 7 TeV, but also from the LHC at 14 TeV. This is a plot from the LHC at 14 TeV. The thing is that you can see here that when you vary, this is a distribution, doesn't matter, but if you go to linear order is only this. This is the box diagram. If you at linear order, they are not box diagram. When you add next to the box diagram, they goes very high, you see. And if you'd say naively, okay, next contribution will be very small, this is a proof where this is not true. And so if you go higher, then you will see that also they have a jump on that. The thing is that I think that the most important thing now is this plot here. The plot here shows the convergence of the theory. Because here the jump is very high. You see that the range, they are 3 times higher than the leading order piece. So then, and if you go, of course here you have almost 0. Whatever divided by 0 would be extremely high. So then it's going to explode. But when you make the ratio, this is the k-factor. K-factor meaning the ratio between leading order and next to leading order. This plot divided by this plot. And if you go by next to leading order over the next to leading, meaning this one divided by this one, then you see that it's becoming flat. So everything it's like kind of matching, you see, because we do not like divergences. So then I arrived to my conclusions. I didn't show you any calculation because it will take long time. So the physics of the Hadron colliders is well understood within the QCD theory. Nevertheless, you have to take into account or keep in mind that you have 2 regimes in QCD: the very large distances or very strong interacting particles, not too small interacting particles. In the free case, in the asymptotic freedom, and in the confinement regime. So I said you have to do an interplay between these 2 in order to make a prediction in QCD. The same. You have divergences or singularities appear in whatever calculation in QCD. So then you have to, before start to cry or start to making, jumping because you are sad because nothing is going well, before doing all of those things, take care of everything. The theory is not that simple, but when you add all together, this is one of the proof in perturbative QCD, you add all together, and then if all divergences cancel, this is a very strong proof of the calculation is okay. There are some other proofs because it could be luck. It could be a matter of luck because sometimes it cancels, and maybe you did also the calculation wrong. But at the end, there are some other proofs that you have to do in order to cross-check your calculations, because at the end the LHC will ask you for the Monte Carlo. Every time you do a calculation here, the LHC will ask you for the Monte Carlo, because they do not, in all the Monte Carlo that the LHC has, mainly they are leading order or next to leading order. And they use the k-factors in order to correct all these things. But the LHC needs to go beyond this, because the errors that they are giving us in the experimental analysis, they are extremely small. So any discrepancy on these numbers are very sensitive from the point of view of in the theoretical side. If you want to make a prediction between the theory and the experiment, always require the perturbative piece and the non-perturbative ones. You glue them together, and then you run all the codes in order to give the distributions. That's the most important thing in QCD. And so the LHC has a huge amount of data, tons of them. Also the Tevatron, but the most precise data sets are coming from the LHC. And so we need that the theoretical community start to work hardly into this computation, because I showed only the next to leading order bit, but next to leading order, it's the Monte Carlo is you have problems everywhere, but once you have everything under control, then the Monte Carlo you have to take into account very seriously the calculations, because that's the key point, because you can check your theoretical computations, but the simulation that you're going to add, the phenomenology, is the most important for the LHC. And then the Monte Carlo distributions are central for any discovery in the LHC. In our times, the problem now is that it's extremely hard, to find new particles by looking at the resonances. Now, the problem that we have is that the Higgs, we look at the resonance, but you know from the theory that the Higgs has a potential. So the potential has mu squared minus lambda phi to the 4, right? So you have to check that the scalar that you put that comes from that theory. And the only way to do that is to test the lambda parameter that goes into the next. It was extremely hard to produce one Higgs. And for order to test the lambda, you have to produce 2 Higgses. So then we think that you have to look into the other direction. You have to look into new estimators, or you have to look into another distributions. And the distribution that that the theoretical community is thinking is to look at the tails of the distribution, because some of the tails have different shapes if you go from one theory to another one, because the peak is there. That's not a problem. The problem is to say if that Higgs is the one coming from the standard model or for any extension of the standard model. So then you have to look at the small deviation. That's the point. And finally, the correct understanding of QCD will give us a clue of the fundamental interaction with the building blocks of nature. And that's all.
Thank you very much, Roger. Questions? Doubts?
Yes.
In the last slide before the conclusions, yes, so you were showing that the ratio between the next to leading order and the next to leading order is getting always smaller when you go to higher orders. Is there an order where it actually converges, or? Okay.
Yeah, this is here. They didn't. The collaboration that did this calculation didn't do the computation of the error bands, because what you say is extremely important. I didn't mention that. But how do you measure the convergence of the theory? You have to compute the error bars. For instance, for the Higgs, between leading order and next to leading order, what happened is that when they compute the variation of the factorization and the normalization and the PDF and everything, then you have the error bars, right? So then you have the leading order error bars do not overlap with the error bands with the next to leading order. So that's why the people ask themselves, if this calculation is going to converge at some point, and the answer was yes. Here, this calculation is not in this plot, but they have shown that the error bars of the next to leading order is, let's say, this one. If you add the error bars, this is not the error bars of the experimentally and everything, but when you add when you put all together, you will see that the leading order in comparison with the next to leading order do not converge. But next to leading order in comparison to the next to leading, they started to converge. Their convergence is very weak, let's say, but they are still in a regime where people think that when you add the n to the cube, then there's going to be not perfect, but a matching between all the others in the perturbation theory. But this is why we go beyond, because it's not important the central value. Here the central value is important, but the most important one are the error bars. How you go, the experiments are going extremely, with the error bars are very, very small, extremely small. And then they also plot in a logarithmic scale, because it's very small. Then the huge variation. So then if you want to make a prediction over these data points, then you have to be extremely precise. Otherwise, whatever distribution, whatever discrepancy, they will show up in this analysis.
No questions? One question. This distribution in the GG minus box, I mean, it starts in 80 GeV because there is some physical reason, or it's just because
no.
the people just started plotting?
Yeah, it was mainly because of the plots of they produce at the LHC, they started from at certain, they made a cut on the PT distribution. So that's why they start at some point. But this is not, they have not a physical meaning. Anyways, you can plot in whatever regime you want. But anyway, they are looking at this particular regime, 100, 120, 100, depending on that.
More questions? Doubts? If not, we thank Roger again. And the next seminar is going to be from